Hello everyone. In this video we are going to talk about failure theories for static loading, and we are going to look at the three major ones that are used mostly in solid mechanics, but this is not an exhaustive list. There is more than these three, but here there are more, but here we're just going to look at these main three well-known ones. And here again, pictures, equations are taken from Shigley's Mechanical Engineering Design. So the first one is what we call maximum shear stress, or MSS theory, for ductile material. And it's also known as the Tresca theory. So this is for material that are ductile, so we can easily form them and they can undergo a significant amount of ultimate or yield strain without failure. Okay, so when you look at the stress versus the strain plot, right, if you look at sigma versus epsilon, this plot can continue for some significant amount of epsilon, okay? Or if you look at tau versus gamma. While for brittle material, you just continue a little bit and then boom, they're gonna break, right? And for steel, this gonna go up and then gonna go down and so on, right? So there are ductile material, they have different behaviors, but this ultimate strain at the break point, at the failure point, is not a small value. So here we are talking about those material like, for instance, aluminum, like steel and so on. For this material, it has been observed, it has been shown that when you put them under tension, so if you have a specimen, right, if you have a piece, shaft or dog bone or anything like that, if you apply tension on both sides of it and put it in a tension machine, then you can see that the fracture lines, the angles are at 45 degrees roughly, and the material starts to lose cross-section in the middle, right? So it goes like this in the middle, as you can see here on this picture on the left. The two pieces, you clearly see that the cross-section is reduced here as you move toward the middle of the part. And this phenomenon, we call it necking. Okay, so the necking happens here. And the angle at which the maximum shear stress is occurring, which is 45 degrees. So if you measure the angle of this line with respect to this direction, this angle, based on theory, based on the Moore circle, as you know, this angle is going to be 45 degrees. And along that angle is what you see the slip lines, or you might call it the Luder lines, which happen at that angle, okay? And this is completely justifiable by the Moore's circle. If you look at the Moore circle, in the case that you basically have only a sigma x, so it's uniaxial, that's all you have, right? There is just sigma x, nothing else. If you look at your Moore's circle, so if you draw this axis and this one, where this axis is basically for your sigma and this axis is for your tau, then basically you have one point here on this plane here that is perpendicular to the x direction. You only have sigma x and 0 tau, so you get this one. And sigma y is 0 in this case, so sigma average is half of them. So this is going to be the center of the circle, and the circle will basically be something like this. Okay, so that is going to be your circle. And in this case, the maximum shear is of course happening on this plane, right? And so the angle you have is this angle here, which is 90 degrees. But remember, in Moore circle, this angle is 2 times the angle of the major plane, right? So this is 2 times the angle of the plane at which this theta is tau is maximum. So since that 2 theta is 90 degrees, then that angle should be what? 45 degrees. So as I said, by Mohr circle, this is completely predictable. And if we want to draw it in general based on the principal stress, what area is going to be the failure area and what area is going to be the safe area? The shape of the failure and the safe region, if you look at the failure region is going to be this hexagon, as you can see, where what are the axes in this case? So here, sigma A and sigma B are the principal stress on the plane. So here, this is for a planar case. So these are all assuming 2D cases. Okay, and but for the sake of the Mohr circle, remember in general you have 3 sigmas. You have sigma A and sigma B, and or sigma 1, sigma 2, and sigma 3, where here it assumes in scenario 1 that the 2 planar stresses, sigma A and sigma B, that you have, the max sigma and the min sigma, are both positive. And what are sigma A and sigma B? Well, in case of 2D, for the Mohr circle in general, let me show you on this graph here. So this is the sigma axis, and this is the tau axis, and this is the Mohr's circle, right? So if you look at the 2D case, then this point here on this side and this side, these are the min and the max for sigma. And in this case, we assume that the bigger one is sigma A, the smaller one is sigma B. So this guy is sigma A, okay, on the plane, and this is sigma B. And sigma 3, the third one, is 0 in this case. So your third one is going to be here. Therefore, the total Mohr circle, which is for general 3D case, is going to be the sigma A is going to be your sigma max, and 0 here is going to be your sigma min. Okay, the minimum is 0, and the maximum is what? Equal to sigma A. And here, of course, in the notation, I call them sigma 1 and sigma 3 instead of max and min. So if that's the case, then your total Mohr circle is basically should be passing through these 2 points. So it is going to be something like this. Okay. So what is the maximum tau in this case? The maximum tau in this case, which is what you care about. Remember, in this method, it says the failure would happen when the shear stress passes the maximum shear in the material. So let's go ahead and add that here, because we did not really specifically talked about it, right? We should have done it earlier, actually. So this method says that, let's type it. It says that failure happens when the max shear stress passes or exceeds the max shear strength of the material. Okay, right? So as long as max shear stress passes the max shear strength of the material, then you can expect what? You can expect failure. Good. So what is the max shear stress? What is the max shear strength? Let's look at those scenarios here. So in this case, as you can see, the maximum shear stress is going to be the radius of the circle, which is the difference between sigma A and 0, or half of sigma A, right? Divided by 2. So if we write it in this case, in here, the tau max is simply sigma A minus 0, right? divided by 2. Good. Now, what is the shear strength? What is the maximum shear that the material can have? So what is the tau allowed? This is equal to the yield strength of the material divided by 2. So as long as this tau max is what? As long as this tau max, let's get a copy of this here. As long as this one is less than that strength, you should be good, right? So if I bring it here, as long as this is less than that, you have no failure. And of course, you can get rid of the 2's. And so you see sigma A, the maximum stress in the plane, should be less than what? Less than the shear strength of the yield strength of the material, which is what you can see here. So as long as sigma is less than Sy, there is no failure. Once sigma A exceeds or equal S, then it is what? Then it is failure. And this is for the case that both planar stresses exist and they are both positive. Which, if you draw this plot here with sigma A on the x-axis and sigma B on the y-axis, that is going to be the first quadrant. In the first quadrant, both of these numbers are positive, and so the bigger one of the two, sigma A, should be what? Less than Sy. So if this number is Sy and this number is Sy, then if sigma A is bigger, sigma A less than Sy means to the left of this line, and if sigma B is the bigger, sigma B less than Sy means what? Means below this vertical line. So that means what? That means this square here. So inside the square you are safe. Outside the square, anywhere in the first quadrant outside the square, there is what? There is failure. Okay? So this is for the scenario that both numbers are positive. Both in-plane stresses are positive. Scenario 3 is similar to scenario 1. In this case, both of them are negative. Okay, in this case, your Mohr circle moves to the left. So instead of this here, now both of them are on this side. So one is here, and one is 0. Okay, so this is 0. And in this case, it says sigma A is bigger than sigma B, but they are both negative. So your sigma A is here and your sigma B is here. So your Mohr circle, this case, has to go like that. And again, your tau maximum, in this case, is equal to sigma B minus 0 or 0 minus sigma B divided by 2. Okay, and this is the tau max that you have, and again, this should be what? This should be less than or equal Sy over 2, and from here you see that sigma B has to be basically bigger than negative Sy, right? For in magnitude, the magnitude of it is less than that, the value of it is bigger than that. So that is this scenario here, which you can see. Now failure is opposite of that. You can see again, if sigma B is less than negative Sy, which means basically on this side, so if this is a negative Sy, if your sigma B is less than that, means here. If it's more than that, means to the right of it. Okay, so this is the, and we can use a bigger than. This is the no failure case, and opposite of that is, which is what you can see here, that is the failure case again. Right? So again, if you want to be safe, you have to be bigger than negative Sy. So for sigma B is above this line, for sigma A is to the right of this line, so that means this area here. So in the third quadrant, again, you stay inside the circle, inside the square. In the first quadrant, you stay inside the square. Now, in case 2, which is either here or here, they are both case 2, in the second or the fourth quadrant, where the sign of sigma A and sigma B are different. So one of them is bigger than 0, the other one is less than 0. In this case, the Mohr circle is going to be like this. So your sigma A is here, your sigma B is here. And your third sigma is here. Again, 0 because it's planar case. In this case, the Mohr circle is going to be like this. And if this is the center of it, then this tau max in this case is sigma A minus sigma B divided by 2, which should be less than tau allowed. And tau allowed, if you remember, was Sy over 2. Again, if you get rid of this, you see that sigma A minus sigma B has to be less than Sy. And clearly, or you can say sigma A to be less than sigma B plus Sy. And if it's equality, that's clearly the equation of a line with the slope of 1 in the sigma A, sigma B plane, with this guy to be your y-intercept or x-intercept in this case, right? So that is clearly this line. And when the sigma A and sigma B switch in terms of sign, or sorry, this guy, it's this one. And when sigma A becomes negative, sigma B becomes positive, then the only change is when these two switch, then this becomes sigma B minus sigma A. So this becomes like that, okay? And that changes the line to this one. So as long as you stay inside these shaded areas, this one and this one, you are safe. So you see, that's why the shape of the safe region in the Tresca method is this hexagon that you can see. Okay, this is the what we call the maximum shear stress theory, or the Tresca theory. And that is based on the Mohr circle, which you can clearly see. Now, this method is a conservative method. What does it mean? It means the value that it predicts, the safe region that it predicts for failure, is typically more than what it should be. Okay, the values of stress that it predicts failure happens, these regions are typically above the reality. What does that mean? It means that in reality, it was observed that there was a point of sigma A and sigma B maybe here outside this, which based on this method means failure, but in reality, they found that it didn't fail. Or there was a point here that they saw, okay, based on this method, that point of stress, the status of the stress is outside this hexagon, so there should be failure, but they saw that the failure didn't happen. So they found that the region that this one gives you, the fail-safe region this one gives you, is smaller than reality. In reality, even outside this hexagon, a little bit outside of it, you still should be safe and no failure happens. That's where the second method, or distortion energy method, came into existence, which is also called the von Mises theory, okay? And this is also for ductile material, okay? And what does this method say? Let's take a look. So I talked about this observation. And one of the things also that was seen in this observation was, if you have ductile material and you stress them with hydrostatic stress, their yield strength was more than what it was in tension stress. And what is hydrostatic? Hydrostatic means the stress in all three directions, x, y, z, is the same. They are all the same value. Okay, so if sigma x equals to sigma y equals to sigma z from all directions, then we call it hydrostatic. What does it have to do with hydro and static? That's because if you have an object inside fluid, so here you have water or something, right? Any fluid, and if you drop an object inside of this, which is small, at all these different angles, as long as the dimension of this is small, all of these pressures, if we call them P1 and P2 and P3, these values are all similar and they're all equal to what? Rho GH plus P0. Okay, this is the static pressure of a fluid at the depth of H below what? Below the surface of the object. Okay, so inside any hydrostatic, inside any fluid that is in a static scenario, at a specific depth, the values at different faces of any element are the same. That's why we call it hydrostatic. Now, what was the conclusion from this? The conclusion was not only the hydrostatic is not really messing up with the shape of the object, it's actually, as you see, it made the yielding in outside this region. So when there was hydrostatic case, I could have failures outside the Tresca region. So this method says it's not the hydrostatic component of a stress that has any effect on the failure. It's the other portion of the stress that causes the material to fail. What is the other portion? So here, if you consider any arbitrary element of the material with 3 sigmas on 3 faces, sigma 1, sigma 2, and sigma 3, and they are not equal to each other, then you can say that this is equivalent to one case of hydrostatic where you have sigma average defined by the average of the 3 applied to the element plus what? Plus the case that the stress on the other faces are sigma 1, sigma 2, and sigma 3 all minus what? Minus average. You can do superposition here, right? You can say that one on the left is equal to what? Sum of these two on the right. Okay. Now what? Well, what's the effect of each one of these stresses? This one is a tension stress all in the same direction, so the effect of this is resizing. This will make the material get either bigger or what? Smaller. Or I can say what? Change in volume. So if all the stresses are positive, then the material will expand in volume. If they are all negative, compressive, then the material would shrink. Like underwater, they are all negative, so the material can shrink if it's really flexible. What is the effect of these guys? These remaining stresses, they will cause shear in the material, or change in what? Change in angles. So instead of making this cube a smaller cube, as we had in the previous case of hydrostatic, you see here, they can make it smaller or bigger. In this case, they're gonna ruin the angles. Okay, they can change the angles and create shear stress. And this method of von Mises says failure happens when these shear stresses are too much. That is the cause of failure. This is not gonna lead to failure. This one does. But how big should these shear stresses or the deformations be before the material fails? In the previous case, it was simple. We said when the max shear stress exceeds the max shear strength of the material, right? But what about this case? What does this method say? It says that we calculate energy. We calculate the distortion energy for this scenario. See how much distortion energy this one will have. And then we compare it against a uniaxial case, like this case here, when the material is under uniaxial stress. And we calculate how much distortion energy this case has until it reaches to the yield strength, okay? Then we compare and we set those two distortion equals for this uniaxial case and this general 3D case. The same, and from there we should be able to find what? A formula for failure. So let's see how this method works. So it calculates, as I said, the strain energy, the energy of distortion, per volume for a simple tension. If you only have a simple tension, it is going to be 1/2 epsilon times what? Times sigma, and again, it's per volume. Okay, so this is the total energy per volume of the material. You can show that it is 1/2 times epsilon, this is epsilon, times sigma. This is for a what? For a simple tension case, right? It's this guy here, 1/2 epsilon sigma. Now, if it's three-dimensional, so you have sigma 1, sigma 2, and sigma 3, so this one is for 3D case, then it is going to be 1/2 times epsilon 1 sigma 1 plus epsilon 2 sigma 2 plus epsilon 3 what? Sigma 3, right? And you know that these epsilons are related to the sigmas through what you know from solid mechanics. You know that, for instance, epsilon 1 is what? Epsilon 1 is sigma 1 over E minus nu times epsilon 2 and 3 added, so it's going to be sigma 2 over E plus what? Sigma 3 over E, where this nu is the Poisson ratio and this E is the Young modulus, right? And similarly, you can write a similar formula for epsilon 2 and a similar formula for what? For epsilon 3. So this guy is like sigma 2 over E minus nu times sigma 1 plus sigma 3 over E, and this one is like sigma 3 over E and minus nu times sigma 1 plus sigma 2 over E. So if we plug in these three right up here and simplify, you get this term here on the right. You get this guy. Okay, you can easily show that. And clearly you see nu is there, E is there, and all the principles. So this formula is the total strain energy for 3D case. But not all of this energy, as we learned, is used for shear. Some portion of it is the energy just for resizing. The rest of it is the energy for what? For distortion. So how much of it is the energy for what? For hydrostatic resizing? Well, in that case, we have to set both all three sigma 1, 2, 3, all of them to be equal to what? Sigma average, which is this guy. If we plug that in, then for change in volume, you get this formula here. So here we plug in sigma 1 equal to 3 equal to sigma average. You get that one, and if you plug in this formula for sigma average, you get this guy. Now that was the total strain energy. If I subtract this UV from U, then you get what? U distortion. So you get the strain energy for the shear case, and that is basically the second line minus the first line minus second line, and you get what? You get this. So this is the total distortion energy per volume, okay, which is only for shear, which is only for distortion. Now we have to go and look at the single uniaxial case here and see for this uniaxial case where sigma can go up to Sy, how much is the strain energy? How much is the distortion strain energy? So in that case, sigma 1 is equal to Sy. As we said, it can go up to Sy. 2 and 3 are 0 because it's uniaxial. So if we plug sigma 2 equal 3 equal 0 and sigma 1 equal Sy in this UD formula, you get this. Okay, and now if we say these two strain distortion strain energies are equal, then this constant term in both of them can be eliminated, and you get what? You get this formula down here. You divide both sides by you take a square root from both sides, and you get what? You get this formula, which says as long as this square root, which is sigma 1 minus 2 squared plus 2 minus 3 squared plus 3 minus 1 squared, the whole thing divided by 2. If this square root is bigger than or equal Sy, that means what? Failure. And if it's less than SY, then it means what? No failure or safe. By the way, this whole square root thing, it has, we can give it a notation. We typically call it sigma prime, or we call it sigma 1 Mises. So another notation for this is sigma what? 1 Mises. And this is what you see in many software packages that do finite element analysis. One of the major stresses that you see in them is 1 Mises stress. So that is this guy here, this square root calculated for you. So first they calculate all three sigma, sigma 1, 2, 3 from the Mohr circle, and then what? The principal stresses, and then plug them here and get one equivalent number. Because here we have three sigmas. We cannot compare each one of those three sigmas with SY. We have to combine them into a single number, then compare it against SY, and this is what Professor von Mises came with. Now, in the sigma A, sigma B plane, clearly that's an ellipse. Why? Because in this case, sigma 3 is 0, so it's a 2D case. So this sigma 3, if that is 0, what would you get? The equation becomes, as you can see, it becomes sigma 1 minus 2 squared plus sigma 2 squared plus sigma 1 squared, basically. Or if you write it, right, it is going to be 2 sigma 1 squared plus 2 sigma 2 squared minus 2 sigma 1 sigma 2 divided by 2. Right? This whole thing under the square root should be less than or equal SY. If we look at the equal sign, so we get the boundaries of the failure region, right? Clearly, we can get rid of all of these 2's. And if you square both sides, that becomes sigma 1 squared plus 2 squared minus 1, sigma 1, sigma 2 is equal to SY squared. And you know this is the equation of ellipse that is rotated for 45 degrees. And that is exactly what you can see here, a rotated ellipse. And an interesting thing about this ellipse is if you draw the Tresca region, that hexagon of Tresca, it falls right inside this ellipse with the corners of it, which are SY and negative SY, being right on the boundary of the ellipse. So this method says not only inside Tresca is safe, actually all of these regions that I'm going to paint in blue for you, all of these regions are also safe. Because these are the regions where the strain energy does not surpasses the one that is for failure, because a portion of it is used just for changing the volume of the material, and not all of it is used for what? For distortion and shear. You see? So the Tresca gives you a smaller region compared to the von Mises. That's why we call the Tresca region, the Tresca method, what? A conservative one. Because it does not allow too much of motion outside this hexagon, but this von Mises gives us a little bit more wiggle room. Okay, so this was what? The von Mises stress, or the distortion energy. Finally, we go to, let's go to an example. You know what? Let's go to an example before we look at maximum normal stress. Let's look at an example together. That might be useful. So here we have a cantilevered beam, a shaft, which is hollow, and there are three forces on it. There is a bending force F, or shear bending. There is axial force P, and there is a torque T. So each one of them will create a stress, and it is a combined stress scenario. The values are given, F is given, the axial load is given, the torque is given. And we want to pick a geometry, a size for this guy, okay, where the material is pre-selected. It is 2014 aluminum alloy. Okay, and the yield strength of this material, SY, is already given, 276 megapascal. So what you need to pick here is the geometry, and the other thing is this geometry, you're going to pick it from the tables, because these kind of tubes, they are specifically picked from some standard tubes, circular tubes, and you want to use a safety factor of 4 at minimum. So what is the geometry that you would pick? Okay, so let's go ahead and work on this problem. As I said, we're going to pick this from standard size tubes. And here I copied the table from the book. And you can see that here these are standard tubes and the dimensions for them are given in inches, right? And this is the dimension that you say 1 by 1/8. What does it mean? It means that, well, 1 inch, as you know, is 25 mils, okay? So the dimensions here, if you look at them, or the properties here you have, is one is the cross section in inches squared, right? That's one, and the other one that, or the two others that you might need for the stress case are I and J, the second moment of area and the polar moment, I and J, as you can see, this one and this one, right? And then you of course have unit weight of aluminum or steel tubing. So if it's aluminum, that's this one. And you also have Z, which is the section modulus. So you have these different parameters here, and K is radius of gyration, which is related to I here. Okay, so we're going to pick one of these. So the top one is for inches, these bottom ones in millimeters, right? So you have these parameters, and we're going to pick one of these. Now, this is all in SI units. So I will try to pick one from this bottom side here. So how much is M? M, of course, changes along this shaft here, but the maximum N you can possibly have is here at basically this cantilever location at this fixed point, and that is F times 120. So here the unit of this is gonna be, because the unit of F is kilonewton, that is millimeter. When you multiply, you simply will get Newton meter. Okay, so the unit of this guy is gonna be Newton meter. So it's gonna be 120 times F. That is the maximum moment that you can have. Why would you pick maximum moment? Because that will give us the maximum bending stress. So what is sigma x in this case? Sigma x is going to be a tensile stress, which is P over A, where A is the cross section of this, P over A plus what? MC over I. What is I? I is the moment about this axis, this Z axis, so this is IZZ, right? Because the moment is about that. And C is the maximum radial distance or maximum vertical distance from that. So in this case, this C is simply the outer diameter DO divided by 2. And here at this top point, you have positive sigma bending. At this bottom point, you have negative sigma bending. And the tensile stress in both cases is just positive. So the maximum stress is on this top point where these two positive sigmas are added together. Now P is 9 in this case, and again the unit is kilonewton. And the unit of A in this case, if you look at that, the unit of this A, as you can see, is centimeters squared, right? Which is basically 10 to the negative 4 meters squared. Right, and pay attention that this guy is kilonewton, so the unit of that is 10 to the 7. And here you have MCI, so this is M, 120 times 1.75, because F is 1.75, and as I said, maximum C is DO over 2, and I here is that IZZ, which you can read off of the table. So if you write it parametrically, this is the maximum sigma x that you can have anywhere on this tube based on a parameter A, parameter DO, and parameter I. This is the maximum what? The maximum sigma that can happen anywhere on this shaft. What about the shear stress? The shear stress comes from T as well as F, but in this case, the shear stress due to F is neglected. Okay, if you have this, you have to find the shear diagram in this, find where the shear diagram is maximum, which in this case doesn't matter. Anywhere you cut, the shear stress is equal to F, and you also need to find the shear stress due to F as well as the one due to the torsion. But here the portion of the shear stress due to the so this is neglected. Why is that? If you remember the formula for that shear stress because of the shear force, that was V times Q over I times T. And this V is the shear force, which, as I said, is equal to F all over the beam. And this one was maximum along this axis. So the maximum of that tau happens here on this axis. The maximum of the shear stress due to torsion, if you remember, shear stress due to torsion is TR over J, where R is the radial distance, T is the torque, J is the polar moment. And maximum of that is, of course, happening as maximum R, which is again D over 2, T is 72, J is given from the table. So this is the maximum shear stress due to torsion, which is basically anywhere on the circumference. So anywhere on that circumference, you have maximum tau, and then this shear stress, basically this one, this tau, if you call this tau 2, this tau 1, and you might call these guys sigma 1 and sigma 2, this tau on one of these elements is going to match the shear stress due to this, because on this element here is this way, on this element here is this way. For tau 2, for tau 1, both of them are this way. So in this point here, you have maximum shear stress. But what is the problem? On that point that you have maximum shear stress, the sigma due to MC over I is going to be 0. Remember, one of these, if you call sigma 1 the bending and sigma 2 the tension, due to tension, sigma 2 is all over the place, P over A. That is not going to change. But this one does depend on that distance C. So here, that MC over I on this neutral axis is 0. And this value is much bigger than this guy. So if you look at where the total resultant stress, sigma and tau, are the best scenario, is still this point here. And in that point, this value is equal to 0 because T is equal to 0 up there. Or sorry, Q is equal to 0, first moment. Okay, also, Q is 0, the first moment. So that one is neglected, but up here, as it's on the circumference, you still have that TR over J. So we calculate that one, and then you have to what? You have to calculate sigma prime. Now sigma prime in this case, remember in this formula, sigma prime is written in terms of sigma 1, 2, 3, but in this scenario here, sigma 3 is clearly what? 0, because it's a planar case. And sigma 1 and 2, if you remember from the Mohr circle, they are sigma x plus sigma y divided by 2 plus and minus square root of basically this. Now in this case, it's not tau xy, it's tau xz, but it was this formula here. And sigma y in this scenario is all 0. So this guy is going to go away. And if you find sigma 1 and 2 from this formula, as well as sigma 3, and plug them into 1 mices, you can write it in terms of sigma x and in terms of what? Tau xz. So in this case, your sigma prime is going to be this guy here. This is the 1 mices stress, where sigma x and tau xy are functions of what? Are functions of geometry. You see, these parameters are missing in them. Good. Now, this sigma prime, the 1 mices stress, should be less than or equal what? The yield strength divided by a safety factor. Remember, in the past we said that sigma prime can go as high as sy. Yes, this is if what? A safety factor is equal to 1. If safety factor is equal to 1, anywhere inside this ellipse you are safe. But if safety factor is not equal to 1, then it has to shrink. So like if safety factor is 2, then you have half size of that ellipse. You're going to have only this for safety factor equal to. 3 means even smaller, right? So in this case, we have to divide that sy by the safety factor given 4. That means the maximum sigma prime is this number. Okay, which is basically 69 megapascal. Now this here has to be less than or equal that. But as I said, the sigma prime depends on 3 parameters, I, J, and DO. So what should we do now? The SY, the material was selected, the safety factor was selected, good, but the geometry not. So now we go to this table and plug in the values I need for A, for I, for J, and also there is a dimension D naught. What is DO? Sorry, DO, the outside diameter, right? And when it says 12 by 2, what does it mean? So 12 mil and 2 means this is your outer diameter, DO, and this 2 is the wall thickness. So that is my DO, that is A, that is I, that is J. If I plug these numbers in, I'll get what? I get a value for sigma x and tau xz, and as a result, I get a value for sigma prime. And then I can check whether that sigma prime is less than 69 megapascal or not. And if we go down this list, all of these tubes from the top would fail. Their stresses would be more than 69 until we get to this guy. Right when we get to this, your maximum sigma drops below 69 megapascal, and so a 42 by 5, if we use that tube, your maximum stress will be 60 megapascal. And if that's the case, then your real safety factor N is going to be 276 megapascal divided by 60 megapascal. It's going to be 4.57 instead of 4. Okay, so your realized or actual safety factor is going to be more than what you wanted, because you have what? You have a little bit more thickness material that you want. But you might not go to this. If you go to this one, your safety factor will fall below 4 here. Okay, so here the safety factor is right above 4. Here the safety factor is still less than 4. So we have to go with this profile. We choose that, and with the material selected, we should be good to go in this case, under static loading. Okay, the last part. The maximum normal stress, or MNS theory for brittle material, which is also known as the Rankine theory, the name of the person who developed it. It says that the failure happens when the max normal stress exceeds the ultimate strength. Let me just type the whole thing and get rid of this bold font. So the maximum, when the maximum normal stress exceeds the ultimate strength, then the material would fail. And again, this is for brittle material like cast iron. And it was observed that they break at 90 degrees with respect to the axis of tension. They break on these flat planes here where the sigma becomes what? The normal stress becomes maximum. Now, for 2D case where you only have sigma A and sigma B and the third one is 0, if you assume that sigma A is positive, right, then sigma A should be bigger than the ultimate strength for tension. And if sigma B is negative, then sigma B should be what? Less than or equal maximum or ultimate strength in compression if it's negative. Okay, so in the negative area on the left side of this axis, as long as I'm to the right side of the maximum compression strength, of course you put a negative sign because it's negative. As long as I stay on this side, I'm safe. Right? And for sigma A positive, as long as I stay to the left of this SUT, I'm less than that, then I'm positive. I'm safe. And if the sign switches, so sigma B becomes positive, then sigma B should be less than SUT, so I should fall below this region. And if your sigma A becomes negative, then it should be in magnitude smaller or with sign bigger than what? Bigger than negative SUC. So as long as you are what? You are inside this basically square, you should be fine where the dimensions are SUT plus SUC, okay, magnitude-wise. So this is what? This is the region for maximum normal stress or Rankine theory. And again, this is only used for brittle material. And one last time, these three methods that we discuss here by no means are exhaustive methods. And there are more methods in the literature, but these three are the ones that are well known. So I just explained them to you based on Mohr circle and everything and the derivation of them. And we went through what? One example to see how they are used. Thank you so much for your attention, and I will see you in the next video. Thank you.